Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on March 5, 2026, just yesterday. It introduces a robot-free, instant policy iteration framework that uses a consumer smartphone and augmented reality to let operators visualize and fix a robot's mistakes without needing the physical hardware, doubling data efficiency compared to offline methods. The paper is titled RoboPocket, Improve Robot Policies Instantly with Your Phone. And as we'll see later, the system shows some really striking data efficiency improvements, with significant implications for scaling robot learning in the wild. So Figure 1 contrasts the traditional data collection process with the new RoboPocket workflow. The left side highlights the previous approach, where operators are tied to physical robots in limited scenarios, creating a prolonged feedback loop that can take hours. The right side illustrates RoboPocket, which decouples policy iteration from the physical hardware. By using augmented reality on a smartphone, operators can visualize the policy's intended actions overlaid on the real world, allowing them to spot mistakes before they happen. They then provide corrective demonstrations that update the policy in minutes. Alright, Figure 2 breaks down the architecture of the RoboPocket system. The left side displays the hardware, featuring a 3D printed gripper that physically mimics a standard robot hand. This rig includes a fisheye lens for a wider view and a magnetic encoder to precisely track movements. On the right, the software interface shows how the custom app acts as a local processing hub. It provides real-time augmented reality feedback, letting operators visualize intended actions on screen and synchronize multiple devices. Well, Figure 3 maps out the entire robot-free, instant policy iteration cycle. The left side illustrates how an operator uses augmented reality visual foresight to spot out-of-distribution states, which are basically unfamiliar situations where the robot's policy is likely to fail. Once a weakness is identified, the operator records a corrective action. Moving to the right side, this new data is instantly streamed to a data-serving node and fetched by a training server. The server performs online fine-tuning, continuously updating the model by mixing new and old data, and pushes the improved policy back to an inference server. This whole loop runs in just minutes, sending updated predictions back to the user's phone with less than 150 milliseconds of delay. Okay, Figure 4 showcases the real-world evaluation tasks used to test the system. Panel A highlights 4 distinct manipulation challenges, covering skills like sorting blocks, folding deformable towels, pouring seasonings, and bagging snacks. Next, Panel B introduces a mouse arrangement task, which specifically validates the data quality and tests how well performance scales with more data. Finally, Panel C demonstrates distributed generalization, where 4 users simultaneously collect data in completely different environments to collaboratively improve the block sorting policy. Moving to the results, Figure 7 compares the performance of RoboPocket against several baselines across the 4 manipulation tasks. The graphs plot the task score against the total amount of training data. The solid green line represents the pure imitation learning baseline, which improves gradually as more data is collected. In contrast, the orange diamonds show RoboPocket's instant policy iteration, which consistently achieves up to twice the data efficiency of the baseline. Furthermore, these charts illustrate that the new method matches the performance of expert manual intervention, marked by the blue squares, doing so without ever requiring a physical robot. Alright, Table 1 details the hyperparameters used for policy training, the specific settings that govern how the model learns. The top rows outline timing parameters, such as an action prediction horizon of 16 steps and an execution horizon of 8. Moving down, we see the core training configuration, including 600 epochs and a batch size of 64. Lastly, the table specifies the observation encoders, highlighting that DynoV2 was used for the towel folding task, while Clip was applied to the others. So, wrapping up, 2 takeaways stand out. First, this system democratizes robot learning by removing the need for physical hardware during data collection. Second, turning a standard smartphone into a closed-loop training platform empowers anyone to easily scale high-quality data gathering in the wild. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.